This is lesson 6.3 on Radian Measure. In this lesson, the focus is on developing the relationship between degree and radian measures of angles. I like this lesson quite a bit because just like we have different languages, French and English for instance, we can talk about angles in different ways, such that we can talk about them in terms of degrees, which you're somewhat familiar with, and also radians, which we're going to cover right now. The first concept we're going to dive into is this concept of arc length. And so in order to get us going on this, what I'd like you to do is consider an angle of 216 degrees. And so what I'm going to do right here is I'm going to draw our unit circle again. So we've been using this unit circle a lot. So let's pretend like that's a perfect circle, unlike what I just drew. And we have an angle of 216 degrees. So we're starting in standard position, and it's going all the way around into quadrant 3. So let's assume that that is 216 degrees, like so. Okay. If we want to figure out what the arc length is, and so the arc length is the distance around the circle from, let's call it this point right here, which I'll call point B, to our terminal point at point P. So if we want to get this arc length right here, how would we do so? Okay, so that's what we're going to take a look at. Well, I want you to, over here, recall something that you know. Recall. You know how to calculate the distance around that circle. That is just known as circumference, and we know that circumference is equal to 2 pi r. But we have something kind of unique going on here, because what is my radius? Well, I told you this was a unit circle. Again, it's pretty ugly, but we know it's a unit circle, so that means my radius is 1. So that means that the circumference of this particular circle is 2 pi. Well, that's kind of interesting. That means that the distance around this blue circle right here is 2 pi. If we use some logic, that would make sense that half the circle would just be a pi, and the other half of the circle would be the other pi, to make 2 pi's. Okay, so if I had to guess what my answer is going to be here, I would guess that it's going to be somewhere between 1 pi and 2 pi, so maybe a little bit more than 1 pi. Okay, so let's dive into trying to think about what this arc is going to be. So I'm going to write arc PB, so that's that little line I have right here, and let's try to figure out what the length of that arc is. Well, if we think about a circle in terms of degrees, we know that a circle has 360 total degrees. Well, how many degrees do we have in this example? We have 216 of them. So we're kind of saying that we have 216 360ths, if you will, like a fraction right there, of our 2 pi, right? Because 2 pi is the distance around the circle. That's basically, you could say, like the percentage of those 2 pi's. And so all we simply have to do from this now is we just have to reduce this. Now, if you put 216 and you divide it by 360, you'll get a fraction of 6/10. Of course, you could reduce that if you want to 3/5. And now we just multiply that by 2 pi. And in lowest terms, we end up getting the 2 and the 10 will reduce to give you a 5. We end up with 6/5 pi. All right? And that kind of makes sense, at least I hope for you, because we realize that half of the circle was pi, and we're going a little bit further, so we've gone a fifth further, if you will, and we get to our point right there. Okay, so that's how you determine arc length. We are always just relating it back to the circumference. All right? Let's go on to talking about this new concept here, radians. All right? Okay, so first let's start by defining what a radian is. So if we have a circle right here, notice that this circle isn't necessarily a unit circle because they're saying the radius is r. So we have radius r, and then also notice that the arc length is r. Well, whenever these match, we have the same radius and arc length, we call this piece of the pie 1 radian. So that distance right there is 1 radian. All right? And what I'd like to show you is how many of these radians we have in a circle. And in order to do that, and we'll get to these diagrams a bit more in a second, I'd like to take you to an animation that I found. So I like this animation quite a bit because what it does here is it first starts drawing our circle, and it says that we have a radius of r, like so. And then it's going to make an arc length that has the same r, like so. And so it says that that is 1 radian. All right, so that's what we've covered so far. Now the question is, how many radians are there in this half circle? Well, it shows you that we could fit another radian, and we could fit 3 radians, and then we'd have a little bit right there. And so I want to pause it, right? Because what they're saying is in this half circle right here, we have 1, 2, 3, and then a little bit for pi radians. Well, remember what we just said about when we were talking about the arc length of a circle? We said that the circumference of a circle is 2 pi. Well, that's interesting that there are pi radians, right? 3.14, if you will, radians on that half circle, okay? And if we continue the video right here, it shows that that would be pi radians, and then it would make sense that we would have 2 pi radians down here, okay? So I thought that was just a neat little animation to show you kind of how this works. So let's go back to our lesson. Okay, so hopefully that that little animation there showed you that half a circle, or 180 degrees, is worth pi radians. Okay, that meant that you had 3 and a little bit of these pieces of pi in that basically half a circle, like so. Okay, and we could go on to say that 360 degrees must be equal then to 2 of them, 2 pi radians. All right. And so from there, what we can do is we can use just a little bit of algebra here to figure out what 1 radian is actually worth. So if we divide both sides by 2 pi here, we're left with 360 degrees divided by 2 pi is equal to just 1 radian. And if we put that into our calculator, 360 degrees divided by 2 pi, we end up finding that 1 radian is in fact equal to approximately 57 degrees, which would make sense why we had, right, because if we think of a half circle has 180 degrees, we could fit 3 of these in and then have a little bit left over. Okay, so that's the concept of radians in a sense. We would say the distance going around this is pi radians, sorry, the distance going around half a circle, the arc length of half a circle is pi radians, and the full circle would be 2 pi radians, like so. Let's take a look at a couple little rules that we know of right here. These 1, 2, 3, 4 we're going to be using in this lesson quite a bit. Another thing that's important to note right here is how we could determine theta. And so theta is can be derived this way. Arc length is equal to theta times the number of radians right there. Okay, and that's what this little diagram was just showing us right there. Is that if we want to figure out what theta is going to be, we are just going to have to rearrange this little equation like so. Okay, so let's go and take a look at a couple of examples where we can play around with this new world of radians. So the example that we have right here says given theta is equal to 170 degrees, determine its measure in radians, and then it wants you to give the exact measure and its approximate value to the nearest hundredth. So let's first start out by saying that we know since 1 degree is equal to pi over 180 degree radians, that was one of the rules on the other side, we can extend that. We can say that, well, we know that 170 degrees must just be equal to 170 times that. So I'm going to go 170 times pi over 180, like so. Okay. Of course, this is still in radians, so we should write that all the way through. And if we multiply these together, we'll have 170 pi divided by 180, which reduces to just be 17 pi over 18 radians. Okay. And so just so you know, we would call this the exact answer. Okay, because of course our answer is in terms of pi. If I wanted you to get me the decimal now, you would just put it into your calculator, and this would be our approximation right here. If you put that into your calculator, you end up getting approximately 2.9, what did it say here, 7 radians. Okay, and so this, if you just want to make note of that, that would be the approximation. Okay, let's try another one. So again, we're using those same rules that we had on the previous page. So this one right here, it says, given theta is equal to negative 12 pi over 11 radians, sketch the angle in standard position and determine its measure to the nearest tenth of a degree. Okay, well, I'm going to start with another since statement. Since we know that pi radians is equal to 180 degrees, how can we use that information to help us? Well, what do we have right here? We are given that we have negative 12 pi over 11 radians. Okay, so we know that pi radians, we can replace that pi with just 180 degrees, so this is the same thing as just having negative 12 over 11, negative 12 over 11 times 180 degrees, like so. Okay, and so if you put that into your calculator, you'll end up getting that this is approximately 196.4 degrees. Of course, it's negative. Okay, and so I think this question said they want us to put the angle in standard position, so let's go do that. So if we want to put this angle in standard position, just remember that it's negative. So that means that we're going to start right here. We're going to go negative 90, negative 180, and to negative 196, like so. So we'll write that as negative 196.4 degrees, okay? Which is equivalent, if you want to do it instead in terms of radians, you could write it as negative 12 pi over 11 radians. Okay? So, finally, using, I believe, a different rule right here, let's go and take a look at this one. So it says, given theta is equal to 7.5 radians, determine its measure to the nearest tenth of a degree. So maybe I should just make sure it's brutally clear here, but these, of course, are the rules that I'm referencing on the previous page. In any event, it says since we know that 1, right, because they're giving you the number of radians, so since 1 radian, we are aware, is equal to 180 degrees over pi, then we can say that 7.5 radians must just be equal to the same thing, just multiplied by 7.5. Like so. All right. And so what we can do right there is we can just multiply these together. So 7.5 times 180, and then divide that by pi. Make sure that we're not using 3.14. I think that's probably obvious for you folks, but make sure you're using the pi button. And I think this one said to the nearest tenth of a degree, and so when you put this into your calculator, we have 430.0 degrees, just like so. Okay, let's keep on moving. If you go to the next page here, what you'll notice I've given you here is I've given you a unit circle. This might be somewhat scary because there's a lot of information on it, but hopefully, probably more than I have time for in this video, but you can kind of play around with this and take a look. What it's going to reference is going to reference some of those special triangles. And so I'm just going to annotate this a bit. You don't have to write this down, but I'll show you that this is based on all those special triangles that I've given you. And then it's also broken it down into dealing with angles. You'll see it has the angles here, and it also has the relationships between radians. So the radians would be like the pi over 6. Well, let's take a look at this one right here. If I was to draw this as a triangle, like so, this turns out into being a special triangle. Do you notice that it has the x-coordinate right here? The x-coordinate, it's saying it's root 3 over 2, and the y-coordinate is 1/2. Well, if you remember, when we had our 30, 60, 90 triangle, the relationship of 30 was 1, and across from 60 was root 3, and then the hypotenuse was 2. Well, if you also recall, this side length right here, that x distance, that's the cosine ratio. Well, think about the cosine ratio of this would be. The cosine ratio would be root 3 over 2, which is why that is my x-coordinate. And then up here would be my sine ratio. Think about what the sine ratio is going to be. It's 1 over 2. So that's how we get these points. Those are the terminal points on our unit circle. So we have 30 degrees, and that is equal to pi over 6. Which basically means that we can fit 6 of these pieces, if you will, right? 6 of those inside this first 180 degrees. All right. So we'll play around with this a little bit to come. I think it's going to help us answer these next questions. All right. So that unit circle is going to be something that I think I'll likely give you a bigger handout because you're going to be referencing that quite a bit. All right. Example 2 says determine the exact value of sine of negative 13 pi over 6. Now, my guess is if you're trying to find the exact value, a lot of you might have just come up here and started trying to look for negative 13 pi over 6, or maybe even 13 pi over 6. And you'll see that we have some that are close, right? That we have 11 pi over 6, but you will not find 13 pi over 6. So we're going to need to do some work to help us figure out how to answer this question. Okay? So I'm going to give you a little note here. And the note that I want you to make in terms of this question is that, yeah, we're looking for negative 13 pi over 6, but it's not on that list. So let's try to use some information that is on that list that might help us. What I'd get you guys to notice is that that is very close to, I think you would agree, negative 12 pi over 6, right? Just a little bit more. It's 1 pi over 6, kind of more in the negative direction. Well, negative 12 pi over 6, if I reduce that, that's just equal to negative 2 pi. And if you think about what negative 2 pi means, right, if I start at 0 and I go negative 2 pi, I've gone all the way around my circle once. Okay, so that means that we know that negative 2 pi must be coterminal to 0. Okay, so that kind of gives us a little bit of a starting point. Because now what we're going to do with that little piece of information is we can say that negative 13 pi over 6, if we just use some arithmetic, that is equal to, right, negative 12 pi over 6 minus pi over 6. Oh, okay. So that's kind of interesting because if we go all the way around the circle once and then we come back a pi over 6, I think you'll realize that we end up at this point right here. Okay, so let's go back down right here. And what do we know about negative pi over 6? Well, we know that it must be, right, because we've just come right down there, it must be coterminal to 11 pi over 6, right? Notice that it matched up with that 11 pi over 6 right there. Okay. So now if I want to know what the coordinates of that point are, I can just look simply right here. And so we can say that the coordinates, so therefore the coordinates are root 3 over 2 and negative 1/2. Okay. And so finally, to answer this question, I'll do the answer in pink right here. It says determine the exact value of sine of negative 13 pi over 6. And if you remember the sine is equal to the y coordinate. And so we would just say that sine is, of negative 13 pi over 6 is equal to the y coordinate right here, which is negative 1 over 2. Okay, and again, that's exact value. We haven't used our calculator to do this. This would be a question where I'd want you to show your work. Okay, so for this one, notice how it doesn't say anything about exact value. Quite the opposite right here. It said round to the nearest hundredth. So whenever you see that, that's kind of a dead giveaway that you must use technology. So that'd be the first thing. I'll get you just a note here. Must use technology. And I don't mean decimals for this, I just mean you need to use a calculator, okay? So the first thing that we need to do is, this is a very exciting moment I'm imagining for both of you, is that we get to set calculator to radian mode. Okay? So up until now, we've always been very scared of radian mode. We always wanted to make sure that we were in degree mode. But now, because we're talking about our answers in terms of radians, right, we can go and make that change. Okay, so once you've gone and done that, we can start answering this question. Okay, so in this question we're given, of course, that cotangent of 12 pi over 5. Okay, and we need to find what the value is at to the nearest hundredth. So you'll note on your calculator, at least on most, that you can't just go and put that in right away. If you remember, cotangent is just the reciprocal of tangent, so I'm just going to go 1 divided by the tangent of 12 pi over 5. So this one is a lot easier. You're just using technology to help you, and you'll end up finding, I think it said, nearest hundredths, you get 0.32. Okay. Let's go on to the next page. Okay, so example 3 here, we have a real-world problem where we'll get to use the information that we've been working on to solve it. So this is an approximate model of the motion of the International Space Station is that it travels at a speed of 27,600 kilometers an hour in a circular orbit at an altitude of 400 kilometers. The radius of the Earth is approximately 6,400 kilometers. Okay, so let's first draw ourselves a little bit of a picture so we know kind of what's going on here. So we have our planet Earth right there. I'll put my International Space Station. It's just going to be this lovely little red asterisk up here. And then let's also denote some of the distances that we have right here. So it says the radius of the Earth is 6,400 kilometers. So I'm going to write that the radius right there is 6,400. And then, of course, this isn't trying to scale very well, but this orbit right here is 400 kilometers, like so. Okay, and so just for our argument's sake, what we're going to say is that the space station right here is going to be, I guess, we'll have it going in this direction, like so. Okay, so it's moving at 27,600 kilometers per hour. So we've set the stage as to what's going down with this question. So let's read what they're truly asking. It says, visualize a line segment joining the space station to the center of the Earth. So we did that. To the nearest tenth of a radian, so we're in radians, through which angle will the segment have rotated after 40 minutes? So after 40 minutes, what's this angle going to be right here? So I think you can appreciate after 40 minutes, right, the space station maybe is going to be right here. So now it's moved and it's just over there. The question is, what is that angle going to be? Okay, so what we first need to do is we first need to figure out what that distance is. How far is this thing gone? So we know from likely dealing with this in physics a little bit that distance is equal to velocity times time. We have a velocity of 27,600 kilometers per hour, and the amount of time it takes, I think it said right here, was 40 minutes. So I'm going to write that in terms of an hour, which is 2/3 of an hour. You don't be careful you don't write it as 40 minutes or 0.4 or whatever. You could have written it as 40 out of 60. Make sure it's in terms of hours. And so then our answer right here, if you'll likely need to use a calculator, we get 18,400 kilometers. So that's what this is right here, 18,400 kilometers. That's how far that station's going. Okay. So the next thing we have to do is we have to figure out what theta is, right? We're trying to figure out what this little angle is right there. So what I want you to recall is that we can find theta using this little equation right here. And so maybe I'll just box this up so we know when we're done with that, and we'll use, I don't know, a different color. Let's go back to using pink. So let's first start by writing down some of our knowns right here. We know that A, and remember what A represents, that is the arc length. So my arc length is equal to 18,400 kilometers. We also know that R, of course my radius, I don't need to write that, but radius is equal to 6,400 plus that 400, so don't forget to add those together, gives you 6,800 kilometers like so. Okay, so how are we going to get theta? Well, one of the rules on that the very first page looked like this. It said that A is equal to theta R. Well, we can use that information to find us what theta is going to be. So theta therefore must be equal to A over R. And I'm running out of real estate right here, but we'll just write it like so. Theta then is equal to my A, which is 18,400 divided by 6,800. And we end up finding that theta, when you put that into your calculator, is equal to 2.7. So approximately 2.7 radians. Okay. So that little bit right there is 2.7 radians. Obviously that's not drawn to scale, but gives you kind of an idea. So make sure when you're doing these word problems you definitely give yourself some type of a diagram like so. Next right here it says, to the nearest 100 kilometer, what is the straight line distance between the initial and final positions of the space station? So they want the straight line distance between there, okay? So we realize that our diagram probably wasn't that close right there, but what you can see is that our diagram would look something like this, right? These are our radii, and then we had our space station right here, and what they want is, rather than this arc right here, they want the straight line distance right here. Okay, well that's fair. So we know that our radius is 6,800, so 6,800 goes here and here. So we have our radius. We also knew that this was 2.7 radians. Now, I know this is going to be a little bit of a blast from the past here, and I don't know how solid you're going to be on it, but whenever we have an angle, so 2.7 radians is still considered an angle. I know it's weird, maybe not seeing degrees, but that is an angle. Whenever you have an angle between two sides, we can use the cosine law. So I'll remind you what the cosine law is. So we can use the cosine law to solve this. So cosine law says a squared is equal to b squared plus c squared minus 2bc cosine of a. And so we can plug and chug our information. So my side I'm looking for, that goes in as your a, so we'll leave that right there. So we have a squared is equal to b squared is 6,800 squared plus 6,800 squared minus 2 times 6,800 times 6,800. And then it'll be cosine of 2.7. Okay, so you put all that information into your calculator. At the very end, remember that once you put all this into your calculator, just like it looks like there, you'll need to take the square root of both sides in order to get a by itself. And you'll get that this is approximately, because it's the nearest 100 kilometer, 13,300 kilometers. Okay, so that's our approximation right there. Okay. So yeah, a little bit of a blast from the past with the cosine law there, but it's fair game. There could be some sine law questions, and so in class I'll probably have to take a look at those a little bit closer with you. Okay, our last page, folks. Example 4 says we have point P, and it's located at -4 and 3, and it's a terminal point of angle theta in standard position. To the nearest tenth of a radian, determine possible values of theta in the domain between -2 pi and 2 pi. So you're used to seeing this more as 360 degrees and -360, but understand that those are the same things. All right. So first, let's draw ourselves a little bit of a picture so we can kind of situate in our head what's going down. So we have a terminal arm right at -4 and 3. So I'm going to write this as a length of -4 and 3. And if you quickly just want to use Pythagoras, I don't know if it's going to help you in this question, but we could figure out that 4 squared and 3 squared gives you 25, so this will give me a hypotenuse of 5. So anyways, that is my point P, right? Now, what does it want us to do here? So it says determine to a tenth of a radian what this possible angle could be, right? So they want theta. So remember how theta starts. It starts right here, and it's going to work its way like so. So what we first need to do is we need to start by trying to find what this little reference angle is right here. Okay. So the ratio that I'm going to choose to use is the ratio that is positive in that quadrant. So if you recall the Castro, we have CA S, and T. So I'm trying to get this little alpha right there. In order to get alpha, therefore, I'm going to use the sine ratio. Okay, so I will go sine of alpha is equal to 3 over 5. Okay, and so alpha, my reference angle, is equal to the sine inverse of 3 over 5. And if you put that into your calculator, of course we're still in radian modes, you will end up getting 0.6435 radians. Okay, so now that I've found out what my alpha is right here, right, I know that that is 0.6435 radians, I have to get what theta is. Remember, theta starts from the standard position right here. So theta then is going to be equal to, remember how these work is you go all the way to the negative x-axis, which remember in terms of radians, that would be pi radians, and then you have to come back that little bit of alpha. So I'm going to write this as pi radians minus 0.6435 radians. If you use your calculator for that, because it said to round to the nearest tenth, we end up getting 2.5 radians. Okay, so that's great. My question is there anything that would have been coterminal to this, this terminal arm in terms of this region? Well, we couldn't have gone all the way around in the positive direction, another 2 pi, because we'd be greater than this. But we could have gone backwards like so. Okay, so if we take this answer right here, so this is 2.5 radians, we could subtract 2 pi radians and get another solution. So theta is also going to be equal to 2.5 radians minus 2 pi radians. So 2 pi takes me again all the way around back to here, and that's still in that region, and we end up getting a second answer of negative 3.8 radians. Okay. So lots of stuff going on there. We had to figure out what quadrant we were in. We had to get alpha, and then we had to find our two answers. Now the interesting thing is we've done this exact same question before in Pre-Calc 11, only we were in degrees, not radians. All right, so B here says given cotangent of theta is equal to negative 2 to the nearest tenth of a radian, determine the values of theta again in the domain between negative 2 pi and 2 pi. So this question definitely has some similarities. Maybe we'll just draw ourselves a little bit of a picture here. I guess we'll start out with cotangent of theta is equal to negative 2. And that goes that we can say that tangent of theta would just be equal to the reciprocal of that, which is negative 1 over 2. Okay. And then if you go and we draw our triangles, so using the cast rule, C-A-S-T, like so, we know that tangent is positive in quadrants 1 and 3. That must make sense that we are looking for something that's negative in these two quadrants. Okay, so those are the two quadrants that we're kind of working on. The question is, what is this little alpha right here? That little alpha, right? So if we want to get alpha right here, we just need to take then the tangent inverse of negative 1 over 2. And when you do that, you will end up getting 0.4636 radians. Okay. So the first thing we're going to do right here is let's go and figure out these two possible solutions. Okay, so I'm looking for this as my theta 1, and I'm going to look as this as my theta 2. Okay, so I'll write this, we'll do the answers in pink here. Theta 1 is equal to, so how do I get that theta 1? It's similar to the one we just did before. You're going to go pi and then minus alpha. So it's going to be pi minus alpha, and our alpha was 0.4636 radians. And we do that, we're left with, because we're going to only one decimal place, I think, yep, 2.7 radians. Okay, so that's my first theta. Theta 2 is going to be equal to, we're going all the way around 360 degrees, or in terms of radians, that's 2 pi. So 2 pi minus 0.4636. And that's going to give me, what do we get, 5.8 radians. Okay. Now, the question is, again, in terms of these angles that we have right here, is there any possibilities of ones that are coterminal? Well, what can we do? If you take a look at this one right here, right, that we first had, theta 1, could we go and do another 2 pi revolution and stay in that region? No. But we could have taken this answer and subtracted 2 pi. And the same thing is going to work for this one. So I'm going to call these theta 3 and theta 4. So theta 3 is going to be equal to that answer, minus 2 pi. And then theta 4 right here is going to be 5.8 minus 2 pi. Okay. And your two answers that you end up getting is negative 3.6 radians. And the other one over here is negative 0.5 radians. Okay, and so underlined in yellow, 1, 2, 3, and 4. those are my 4 solutions for this question. Okay, so what I always like to do, like I said, is find my first answers and then see if I can add 2 pi and fit it in that region. Sometimes you can't, like this, if the ones are positive to start with. Sometimes you can if they're negative. And then also try to subtract 2 pi and see if they stay in that region. Okay. So that concludes this lesson. A couple of new things here. We were learning about arc length and radians.